So in the last video, we created the 3D model from scratch of this transformer. Now we're going to use that model to try some parasitic extraction and look at some of the parameters like the magnetizing inductance and the leakage inductance, some of the capacitances of this transformer. So let's check it out. Now we just want to assign the materials. So we can right click on this, assign materials. So here we're in this personal library. We want to get back to select all. We can select air for this one. For the core, we want to do this one that we've already defined previously. It's MPP 200. And for these guys, we want to do copper. So now that the materials are set up, we can do the excitations. And we'll just change this to face. So we want an excitation in here. We just right click, assign excitations, current. And for this, we'll just do 1 amp, I guess. We'll call this primary. This is the positive. And that's going into the top here. You can see the arrow. We'll do the bottom here. Got to move it up so you can see it here, but we're going to assign the excitation current again, and we'll swap the direction so it's coming out of the bottom, and this will be primary in. This is 1 amp. And we're just going to leave the secondary with no excitations for right now. And then for parameters here, we want to assign a matrix. And we're going to just select this primary for the matrix. And we'll call it primary. So that should help us get some inductances. We can save that. And now it's time to add an analysis here. So we'll do a solution setup. And we're just going to do everything default for right now. We have that setup 1. And now it's time to do the mesh. So let's just try the default mesh and we'll see how long that takes and what it looks like. So we'll right click down here under analysis and do generate mesh. Alright, so the mesh is done here. We can right click on this. Well, let's see, right click on this one here and we can do mesh statistics. You can see here it made 425,000 elements, and here they are. It took 17 minutes to create the mesh. So if we right click on fields and plot mesh, we have to select it. So let's select these two. Or 3 and plot mesh. So here's the mesh. It's a little easier to see if we hide these guys. So you can take all this stuff and hide in the active view. There's the mesh. And it actually looks like it's pretty smooth. So I was trying to do this with a smaller transformer with more small wires, and the default mesh did not work at all, and it took hours and hours and made terrible looking meshes with spikes sticking out of them. So I feel like we got kind of lucky on this mesh here. But anyway, if you do need to adjust the mesh settings, I'll link in the description a slideshow PDF that talks all about meshes from Ansys. But you can either right click on the geometries by getting in the object selection mode. We have to make it so you can view these guys again. View, show in active view. Then you can click on them and you can assign these mesh operations. There's on selection, inside selection. And then but before you do that, you can just go to mesh settings up here in the simulation, and you play around with these. You can try the tau, try the classic. One thing I noticed, if you want to really make it a simpler mesh, you can go in here and do set the length and dial this back so you have like 0.01 millimeters. It starts it off pretty fine. I noticed that ComSols, if you bring it down like this in the ComSol slider, it makes it real coarse, real easy. But in here, you really have to go in here and reduce this set length. And then if you want to get it to hug the edges more, you can do this curvilinear thing, or you can do like classic, go in here and change these degrees so that it deviates less, like 5 degrees. That'll make it hug the curves a little better. Well, that takes a lot of experimentation. So now that's all ready, we can run a validation check. Looks like everything's ready, so we can go ahead and analyze all. So that simulation failed, and this is the error message that it gave. Current leak to the air, simulation completed with execution error. So I fiddled around with it for a minute, and then I realized I didn't do this region here, this bounding box. So we have to go up here to draw and add this bounding box, and then percentage offset here, we're just going to say pad all directions 0. So that's going to make a box that exactly fits the air cube. And we can check that with this measure position. See, it's 10, 10, 10, so it's just like the air cube. And now save that. And when it pops up with this thing, it's saying, do you want to save all of your history? And that's like the history of building the geometry. So ComSol automatically saves all that all the time, but Maxwell kind of wants to get rid of that, which seems kind of like a bummer because then you can't revert any of it. So I just click don't show this again and save without cleanup. So I don't want it to clean up. So it's going to invalidate the solution. So that's okay. And now we can go back here, double check that it's still good, and analyze all. All right, so that simulation finished. It looks like if we go over here, it took 34 minutes. So that's not too bad. And now we can go down to the results and do a magnetostatic report, rectangular plot. Now we'll do a data table, and this way we can check the inductance. All right, so here's the inductance. It says 9.6 microhenries. I think that's what we got for the same thing in ComSol. But if we look at this, 90 nanohenries per turn squared. So for 100 turns, that'd be 9 microhenries. So 9.6 makes sense. All right, so that's the open circuit test. For the short circuit test, let's just save a whole nother project here. So we'll just save as, I'm gonna call this short circuit. So go back to here. We can hide that region now so it's not in the way. If we select this face here, we want to get on face. So right now we don't have any excitations on the secondary. I want to assign one to the positive here, and this will be a voltage, and we'll just say 0 volts. Call this secondary P. Yeah, we can just make this volts. And this one here, we're going to assign a voltage to that one too. And we'll make that 0 volts. So since there's 0 volts on both of them, that'll be a short circuit. And now we can go to the simulation, do our validation check. Everything looks good. Save that. And we'll go ahead and analyze all. Okay, so that finished. I don't think that worked. Let's go here. We can update report. And we're still getting 9.6 microhenries here. So that's not showing us the leakage inductance. Yeah, I was thinking we forgot to make a matrix here, but there's still only primary. It's not letting us do secondary, even though we put a voltage source. So it's only showing things here that you have a current source on. And just to be sure, let's delete this and we'll make a new data table. We'll make inductance, yeah, so it's only got the primary. So I think this is a little bit different. I think what we actually have to do is we can get rid of these two secondary ones. I don't know if it makes a whole lot of sense, but we need to assign a current excitation here. And I'm just going to make it 1 amp. It doesn't really matter. We're going to make it the secondary. And we'll just make it polarity the same way. So this one will go in. It's kind of at a funny angle there, but it's going in. And then this one here, we'll right click, assign excitation, current, and this will be coming out. Secondary in. Make this 1 amp. You can see it's coming out there. Okay, so we have these two on the top going in, and then 2 on the bottom coming out. So this isn't really how the transformer would work necessarily, but we just have 1 amp in each of these. Got rid of the results and the parameters here so we can re-add this matrix, assign matrix, and then we just want to have the primary. Now we have the primary and the secondary. So just click both of those, and there's this post-processing thing. You can add these together and make a group, but we don't want to do that. That's just going to add everything together. So that's like if you had multiple geometries that together made up the primary, you could link them up into a group. But this one, we'll just leave it matrix 1. And now we're ready to run this again. All right, so that finished running. We can check out the time again. It took 15 minutes. So we go into the matrix here. Let's see, we can do results. Create magnetostatic data table. And in here, we've got coupling coefficient, got the matrix. Okay, so now we have primary, 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 secondary. We have these 4 combinations in the matrix. We can do a new report for that. While we're here, let's just do the coupling coefficient, and we'll check out this nominal here. So the first thing to notice is this nominal table here is the same as this L table. So 9.530 here, 9.530, 9.606. So we can just look at the L table, and this is a little bit different than what we're doing in COMSOL. So in COMSOL, we were directly measuring the magnetizing inductance with the open circuit test, and then the leakage inductance with the short circuit test. This is just making a matrix, kind of like we were doing the capacitive matrix in COMSOL. So we're getting here the self inductance primary to primary and the mutual inductance primary to secondary. We also have this K factor here, this coupling coefficients. So our K factor is 0.992 between the primary and the secondary. It's just 1 from primary to primary because that's just itself. This K factor is what you could put in the SPICE coupling coefficient, but our model doesn't use a coupling coefficient. We're modeling the magnetizing and leakage as separate components. If we go back to the L here, For all intents and purposes, this mutual inductance here is basically our magnetizing inductance, and our leakage is just this minus this. So that would be 606 minus 530 is 76 nanohenries. So we do kind of the same thing if we use these coupling coefficients. So this is 9.606 here, and if we multiply that by 0.992, then we should get roughly 9.530. So this is not the best example since both the primary and secondary have the same number of turns, but we have this for our magnetizing, and then we have our leakage of 76 for the primary and the secondary. Okay, so to get the capacitance and the DC resistance, we're going to have to do a couple more simulations, and I renamed this toroid transformer all. I'm going to add a couple more solutions in here. So if we look at these solution types, so the magnetostatic is what we just did. We want to do an electrostatic to get the capacitances, and then a DC conduction to get the resistances. So what I'm going to do is just go back to the desktop here and add a whole new Maxwell design. And I'm just going to rename this one to Inductance Analysis. And I'll call this one Capacitance. So for the capacitance one, we're going to change the solution type to electrostatic. Here we have all these models and stuff, so I want to copy this model. Let's see how we can do this. So we can't copy that way. If we go back here, I'm going to try just copying this level here, Control C, and we'll go back. Somehow we can copy this stuff. All right, looks like that worked. So we got the geometry and the materials here. Can save that. We have to go back here into the air and view, hide an active view. And we have this box too, we can leave that for now. So now we have the geometry, and we need to reset up the excitations. We're going to click on, for this one, I'm pretty sure we can do object, and we can assign a voltage to the whole thing. We'll just make this 1 volt. Just do 1 volt for the secondary too. Now I'm not sure if it's required, but I'm going to put an excitation on the core of floating. And we'll just say 0 coulombs, and then for the air, I'm going to assign, so they don't have a way to ground the air in here. So I'm not going to worry about that. I'm just going to save this and then go for an analysis. We'll add a solution. We'll just use the default. And we'll just use the default mesh for this too. And just give this a check here, validation. So it says everything's okay. So we want to go in here and assign a matrix. Get both the primary and the secondary. And now save that, analyze all. So it came back with this error. The name primary appears more than once in this project. The name should be unique. So I don't know if that's because I have geometry here and in this one, or if it's due to this excitation. So I'm just going to rename this excitation primary. I'll just call it primary all, secondary all. This doesn't make a whole lot of sense, but see if it likes that better. So that one's done. So it actually did work to just rename these. I guess it didn't like that these had the same names as these geometries over here. It did take a long time, and it said here that it didn't converge with adaptive passes at one point, and then it switched to like a direct solver. And it took a really long time generating the mesh. But if we check this out, profile, it is 3 hours and 21 minutes. So let's see what it did here. We check the results. We'll do data table. And I'm just going to make a new report for everything in these two matrices. So the coupling is just 1 and 0. So this matrix here, if we check out some of their online stuff, it says the capacitance matrix is C11 plus C12 and then minus C12 here. So this is C11 plus C12 here, and then this is minus. So this is basically 0. So it looks like it's saying 93 picofarads is the mutual capacitance. And I think we got like 4 with COMSOL. So I think I want to run this again. But I think that for the primary, I did 1 volt, and for the secondary, I did 1 volt. I'm going to change a few things. I'm going to do 0 volts for the secondary, and I want to also see if I can speed it up a little bit. I'm going to go to this setup here, and I'm just going to double the number of passes, and I'm going to double this refinement here to see if it'll hone in a little faster on the solution. The other thing I want to check out is, does the air material have any conductivity? So it says bulk conductivity is 0. So I think I'm going to make this 1, because 1 is pretty close to 0 compared to the copper, which is thousands. This relative permittivity, yeah, I'll just leave that. While we're checking it, I'm just going to see what the conductivity is of this. So the conductivity of the core is 0 as well, so I'm just going to make that 1 and see if that helps it converge a little better. All right, now we're ready to do our check. Go ahead and run it again. So that simulation failed. So I think if we check this out, it's got not a number here for all the results. It took a while too. 11 hours. I noticed it's using a whole lot of RAM too, so I think that might have been part of the reason it's taking a long time before, is because it's maxing out the RAM and starting to use the hard drive. I was thinking about the not having a ground excitation, and I think assigning stuff 0 volts is probably just the same as ground. So I'm going to go over here to the air, and I'll just assign it an excitation of 0 volts. So, but we'll call it something different so it doesn't get confused. And I'm going to go back to the analysis setup here. I think the passes is fine. Maybe I'll lower this back to 40 or something. Put minimum number of passes. I'm going to do like 5. So I've got this warning that these excitations overlap. So I guess assigning the error to 0 volts is not really going to work. So I'll just get rid of that again. And we'll go ahead. All right, now everything is green. So I'll analyze that. I'm just going to close all my extra programs so I can have as much RAM as I can so that it simulates as fast as possible. So that simulation was taking a crazy long time, so I aborted it. I'm going to go ahead and check out the resistance here. We can come back to that. So I'm going to do desktop and add a new 3D simulation. So here it is. And I'll rename this one resistance. And this one is going to be DC conduction. So we'll go back up to one of these. Copy all of these. Control C. Control V. Okay, so I think I had to click in here and do Control V for the paste. I just deleted all the excitations that we copied over. I'm going to add some new ones, so I'll do a current here. I think since these are just both the same, I'll just call this 1 amp going in to the primary, and I'm just going to set primary in as a sink, so that'll just sync whatever current's coming out there. I'm just going to leave the secondary disconnected for now since they're both exactly the same. Let's see if I go to validate. So I'm getting these errors here. Solve inside cannot be set for an object that is excluded due to material threshold constraints. So I think I have solve inside set for all this stuff. For this analysis, it doesn't really need all this stuff, so I guess we could just delete it. But I'm just going to click this air and this core. I'm going to uncheck solve inside for the things that don't have much conductivity, so it's not trying to solve the internal volume of them. Let's see if that helps. Clear these messages. Now it's got this weird error talking about memory leaks and access violations. I think I'm just going to restart the whole program. All right, it seems to be happy after I restarted it. So let's just go ahead and analyze all. Okay, so that one only took 19 minutes. So it looks like you need to do this field calculator on here to make any measurements of what the voltage and currents are here to try and calculate a resistance. And I couldn't figure out how to do it with all of these. So I could try doing a voltage across here and maybe it would be easier to figure out the current flowing through here. But I think at this point, I'm just going to go back to here and try the Q3D extractor because that's supposed to make all this stuff easier anyway. So that's it for trying to extract the parasitics manually. I didn't get as far as I was hoping with that, but I think at this point we'll just move on to the next video, which is going to be using the Q3D extractor tool, which is supposed to make all this a lot easier. So once I get that video up, I'll have it pop up here at the top and put it in the playlist. So I'll see you next time. Thanks.